All right, well, it's a pleasure to welcome our distinguished alumni speaker, Dr. Campbell. I imagine he probably doesn't need much of an introduction, but I'll give one anyway. I've known him for a while. I think it's fair to safe to say he is a distinguished alumni. He probably have more degrees from the University of Maine system than most people.
I don't know if that's a good thing, but
well, hey,
slow.
Right. So now is an assistant professor in the Climate Change Institute and the School of Earth and Climate Sciences, and he's going to tell us today about the Juneau Icefield research program.
All right. So today I'm going to talk about something that's near and dear to my heart, and I'm going to set the stage. I'm going to try to persuade people in this room that something we're doing on the Juneau Icefield is probably one of the most important things we should be doing. And I'm going to set the stage by starting out recognizing someone that's sitting right in the front table here, Dan Churchill. About, 10 years ago, Dan and I had a conversation. Dan funded me on a project, and watching all the presentations yesterday and today, seeing all the students that had field experiences as a result of Dan and Betty's generous donation to Maine and Dickinson as well, it is a pretty impressive feat over the years, and it got me thinking about what kind of inspired me initially in terms of getting into the field, and I couldn't help but find this photo that my mom sent me. Pretty embarrassing, but this is me right here. This is also me. I'm not sure if this is great parenting at the time, but what inspired me to get into the field, to get outside, to see nature, to see things moving down a river system. I was very lucky, and I think it's safe to say that everyone in this room is extremely lucky to be where we're at today. And so what I'm going to talk about today is a program, this is me 28 years later, kind of trying to pass that excitement on to students in a school system in Maine. And what I'm going to talk about today is a program that we now have affiliated with the University of Maine called the Juneau Icefield Research Program. The program was started by Maynard Miller, who's here on the left-hand side, and it has a long history I'm not going to really dive into, but what a phenomenal inspiration to about 2,000 students over the years. He directed the program from 1946 to 2006. Which is an unbelievable, 2009 actually, which is a pretty unbelievable record. I also have a picture here of his wife, Joan Miller. I think it's important to state that she was a driving force in terms of a lot of the behind the scenes work to keep this program thriving and surviving. And as I mentioned, over 2,000 students have been inspired by this program and represent a large number of people that are senior scientists in the community today, in the polar community. And so I want you all to kind of think about what inspired you as I talk about the Juneau Icefield. What got you into the field that you're in now? What was that first inkling, that first excitement that you got? And we're going to talk about what we're doing on the Icefield now and what we see is using the Icefield from a value to the University of Maine and our broader polar community moving forward. So the key take-home point that Dr. Miller really did a phenomenal job with people on the Icefield is it's really a collaborative effort. He had this thought process of this teamwork to accomplish the science on the Icefield together and to safely traverse this Icefield together. That was a big kind of component of his philosophy on the Icefield. And we use that today very much so. And I think it's a little bit of a shift from our thinking in science today. We're all competing for NSF grants or NASA grants. And behind the backs, we secretly don't want our competitor to get their grant because that will impact ours. But we're very nice to each other at face. The beauty of this program is we have basically this year 84 people attending the program, and we're all collaborating towards a common goal. We come from our committee, our group that is going to be on the Icefield this year comes from around the world, and they're really working together to basically do real science in the field with students. It's a lot of near peer mentoring experiences for students, for faculty, for young early career faculty. So that's kind of how the program has been set up over the years. So this was last year, 2018. I've mentioned there's over 2,000 students that have attended since 1946. You'll note something really exciting. We're on a nice upward trend, and this is a trend that apparently we're seeing in field programs. We're getting more female enrollment. Consistently, we hear inspiration from students coming out of the program. That's what they consistently say in their responses, that they're inspired from being with this program. We have a lot to do, and I'll talk about what else we have to do and what we can do moving forward, though. The program itself, if you've never heard of the program, we start in Juneau, Alaska, and we traverse all the way to Atlin, British Columbia over 2 months. We spend, and this map is kind of the traverse itself. So we spend about 4 or 5 days in Juneau learning field safety skills. Then we traverse up onto the ice field through a pretty big hike to get to this first camp, Camp 17. We spend 10 or 12 days there learning more field skills, starting to get introduced to the science. Then we traverse a couple days to this Camp 10 region and spend 2 weeks or so in the center of the ice field conducting research with a variety of scientists. We then traverse up towards Camp 18, spend more time at 18 for about 10 days, traverse up and into Canada, down the Llewellyn Glacier, spend a few days at Camp 26, hike out on the blue ice to Atlin Lake, and then we catch a boat in Atlin, all the way back to Atlin, the town of Atlin. It's about a 30-mile boat ride. Spend a few days in Atlin, talk with the community members, students give presentations to the community, and then we catch a ferry all the way back to Juneau. So that's the overall traverse. During the traverse, we spend about 6 weeks on the ice. I should mention, I'm pointing out these primary camps, Camp 17, 10, 18, 26. There's actually about 11 sites on the ice field that have buildings, and I'll show a few of them. We basically have students doing research-based education the entire traverse, and I'll talk a little bit about that research. And the key point is this is now a 6-credit program at the University of Maine for students to take. It's also for students from around the world to take. We have 32 students right now that max one program, but our goal is to try to expand that to have multiple programs. We have about 8 field staff. We have 35 faculty coming in from 20 different institutions. We have 7 medical staff, and we have 8 funded projects this year that students are going to be participating in, and I'll talk about those. And as I mentioned, we have 84 people coming this year, so a pretty big program. For reference, the New Zealand program is about 80 to 90 people in Antarctica, so it's a pretty good sized program. These are examples. I'm going to flip through these slides pretty quickly, but these are examples of some of the camps. This is the first camp, Camp 17 near Juneau. Camp 10 is our biggest camp, right in the center of the Juneau ice field. It can house about 60, 65, maybe 70 people. Camp 18, my favorite camp, overlooks the Gilkey Trench, a pretty phenomenal view. And then you're getting into the continental side of the Juneau ice field. You can start to see grasses growing on the other side, on the Llewellyn Glacier side. This is Camp 26. And then in Atlin, British Columbia, we actually own the old hospital building that we use as kind of a base in Atlin. So what's important about the Juneau ice field? There's a few things that we think about. First of all, Juneau ice field in general and all of Alaska are contributing a fair amount to global sea level rise in terms of mountain glacier systems. One thing that's pretty interesting, though, is you'll see the Taku Glacier here in blue. It actually has been relatively stable over the past several decades, but the rest of these glacier systems are all losing significant mass. This is some data from our colleague Chris McNeil, who works with the U.S. Geologic Survey, and Shad O'Neill, showing mass balance records from the Lemon Creek Glacier and Taku Glacier. And I should mention that these 2 glacier sites are 2 of the longest studied glacier index sites in North America and, in fact, the world. So they represent boots on the ground studying these glaciers since the mid-1940s to early 1950s, which is one of the longest records that we have available. You'll notice Lemon Creek Glacier in the orange here. This is the area, has been declining steadily, has lost about double the area since the mid-1940s. And in terms of annual balance, it's lost over 40 meters of elevation. And you'll notice the Taku Glacier has actually gained some mass. And then if you look at, gained some area, and then kind of leveled off. And if you look at the actual balance itself in terms of elevation, you'll see it's starting to lose a total balance. Very recently, we think we're actually capturing the start of the decline of the Taku Glacier. This is another cool schematic of data that's been collected in the past 20 years or so, looking at the Gilkey Trench that actually sits below one of the camps, Camp 18. And this is collected by our colleague Scott McGee and students. And basically, this is a centerline profile. What this is showing is centerline elevation profiles between 2001 and 2017 on these, we call them ogives. And you'll see that you've lost about 40 meters of elevation over that time period. So pretty significant. And you can see the trim line right here where ice used to be, and I think some historical photos go back to the 50s or so that show about 200 meters of elevation loss. So pretty significant elevation loss in total ice volume. And I think one take-home point I didn't mention, these glaciers all sit right at about 0 degrees temperature. So they're really touchy with temperatures. So they really are a pretty decent indicator in terms of rapid response because the ice sits right at about 0 degrees temperature. They're temperate glaciers. So I don't have to harp on these types of studies to this room. We have a lot of people here that are studying a number of these aspects. So I'm going to flip through these slides fairly quickly, but we know in the Arctic we have polar amplification. So these plots just simply show warming temperatures. So the reds represent warming temperatures between 1960 and 2013. If we just shorten that time period between 1990 and 2013, you see darker reds. That means it's ramping up, it's speeding up, that warming process is speeding up. Well, what's that doing? Well, it's changing global water budgets. So reds represent areas where we're losing water over the period of time. So if we think about Alaska, we have this big kind of red blob here, Greenland. The Arctic is really losing a lot of water annually as a result of this increased temperature. It was really, for those of you who attended Susan Kaplan's talk last night, she mentioned that she was talking about Perry's expedition to the North Pole. I thought this was a nice little tie-in to that and changes in annual sea ice cover. This is a really cool NASA visualization showing sea ice in the Arctic and how it's changing. And you'll note the whiter colors represent the older ice packs, and this is running from the 1994, I believe, up to 2016. As it continues to cycle, just watch how much of the annual sea ice and the older sea ice has a tendency to disappear. And you'll see that it is rapidly disintegrating over time, and in particular the most recent decades. And that has some ramifications that we're also concerned with in terms of Arctic environments. One of those ramifications is impacts to coastal communities. That reduction in sea ice allows for an increase in wave action, which can then therefore exacerbate coastal erosion processes. So now we're getting into more recent times. You can see that sea ice is rapidly disintegrating. I'm going to bounce it forward just for time's sake. So this is a time lapse of that rapidly disintegrating coastlines that I just mentioned. These are permafrost frost wedges that have busted off as a result of wave action and thawing. And these blocks are thawing. They're about 10 meters in diameter, and they thaw over 9 days. And what we're seeing in some areas in the Arctic and the coastline, you're seeing thawing of up to 20 meters per year on the coastline in terms of degradation, which is pretty phenomenal in terms of rate of retreat. A few things that we don't know. We don't know how much CO2 and methane are stored in permafrost. We have very little knowledge about permafrost. I've spent probably 30 field seasons doing permafrost studies in the Arctic and in Alaska, trying to help other scientists quantify just where permafrost is and where it isn't. That's one basic question that we still struggle with. The reality is, in shoreline perspective, permafrost represents about 100,000 kilometers of shoreline worldwide, which is about 34% of the world's shorelines. So a fair amount of important terrain that we're talking about here. There's big societal impacts here. I mentioned the soil carbon loss. This is a model that projects soil carbon loss into the future. And you'll see the areas in red basically represent areas of changes of soil, greater changes in soil. You'll see that Alaska, kind of Arctic Canada, are areas that are predicted to lose the most in coming years. So obviously a big, important consideration to think about. And I mentioned Alaska, but this is just a different display of Alaska glaciers. I've talked about Alaska glaciers briefly, but if you look at some numbers suggesting what mountain glaciers are losing the most mass, again, Alaska's right there at the top, and then you have a couple more systems in Arctic Canada. So these are the changes that we're seeing as a community, as a science community. The key take-home point is all these changes are interrelated. They're all complex systems, right? They're coupled Earth systems. And basically the Juneau Icefield focuses on teaching our students about those coupled systems while doing research in a variety of fields. So this is a nice publication that Shad O'Neill came out with, a really nice sketch by Kristen Tim on the paper recently in Biogeosciences that basically summarizes what we think is going on in Arctic Alaska, which has a lot of similarities, not quite similarities to Maine because we don't have glaciers here, but it does have a lot of similarities to Maine, considering Maine has the fastest warming ocean in the world, right off the coast of Maine. We have a fisheries off the coast of Maine. They have a really important fisheries off the coast of Alaska. So there's a lot of similarities, and we know there's a lot of teleconnections between the Arctic environments and our location here in Maine. So thinking forward, I've shown some plots from the Juneau Icefield that suggested some of the long-term data sets that have been collected on the Juneau Icefield. Very important data sets to kind of give us spatial and temporal understanding of how glacier systems are changing, for example. But I mentioned there's a lot of teleconnections in terms of the studies that we're conducting between things like glaciology and permafrost and ecosystem science. So as I mentioned, we have students that are studying each of those aspects, and this is just one figure that a student put together, one of our artist in residence students, kind of summarizing elevation loss on the Juneau Icefield and one of the glacier systems. We're doing atmospheric science studies on the Juneau Icefield, right? Glacier retreat is a direct correlation to how you have atmospheric circulation patterns changing over time, where warm temperatures are coming from, where you have water evaporating from the ocean and being redeposited in different locations. As that changes, you're going to have changing precipitation patterns. We know from work that Dom Winsky, where Dom's around here somewhere, came out with recently that we've had significant increases in atmospheric temperatures in the Arctic and significant increases in accumulation, but that increase in accumulation is not enough to account for the melt that occurs in the summer, right? So those are the types of things that we're starting to think about when we're thinking about the Juneau Icefield. So this is a plot from our students from last year, and also working with our colleague Brad Markle, who's at Caltech now. Basically, they're just collecting isotope samples, coastal, where my dot is here, going continental, and you have a change in water isotope values as you go towards the continental climates. And they've basically modeled, as a result of that atmospheric trajectory modeling, where they think this precipitation originated from or originally evaporated from. So again, they're trying to get at an overall picture of atmospheric circulation using snow chemistry on the ice. I mentioned polar ecology. How does polar ecology fit into the equation? Well, this is a beautiful sketch by another student, Abby Case, last year, that kind of outlines succession of vegetation in deglaciated areas. And we have teams that are coming to the icefield studying vegetation succession, natural vegetation succession, and how that progresses over time. One big question is, how is that going to change over time? As you have drier environments, less precipitation or more precipitation, how do your Arctic communities evolve over time? This is a paper from Kimberly Miner, who graduated from Maine, and now she's a research assistant professor here as well. She also works for the Army Corps of Engineers. And she effectively was looking at organic pollutants being deposited in glacier systems in various locations of the Arctic. So she did some work in Switzerland, I believe, and then she's done some work in Alaska with us as well. Well, we're doing something similar. We're effectively looking at the potential for pollutants that have been deposited in the snowpack and the ice that are now melting out and basically being transported down glacier and into the downstream ecosystem. The question that Kimberly has been looking at is, how is that impacting downstream societies? Thinking about native populations that thrive and survive on fish species significantly that might be bioaccumulating those pollutants. Those are the types of questions that we're interested in talking about on the Juneau Icefield, and we're interested in researching, and that we are pursuing. Another topic of discussion. Amazingly, we've been traveling to the Juneau Icefield since 1946, and until relatively recently, we haven't had a really easy way to study ice thicknesses. Radar has been developed for a number of years, but there's a number of complexities in terms of using radar in mountain environments to measure ice thicknesses. And one of the big take-home points with the paper up here, the consensus estimate of glacier ice thicknesses distributed around Earth, is that these large mountain glacier systems are pretty big question marks for us. Because we don't quite get the geometries right. So we're trying to do a number of things like modeling, collecting some geophysical data, and doing some numerical modeling. So for example, on the Icefield, we're using some pretty sophisticated radar systems to measure ice thicknesses. This is an example of ice thickness radar profile. You can see this is ice thickness on the side, and this is the actual bedrock here where I'm outlining. So this is all ice. But then we're also starting to move towards modeling that perspective. So if we have some known ice thicknesses across the ice field, we can do some sophisticated mass conservation calculations with numerical models to calculate how much ice volume is there if we know other things like ice flow velocity measurements, and we have our mass balance records, as well as some ice thickness information. So we have a team that's starting to get involved to actually model that and ideally import that into existing estimates to try to update our estimates. Well, why is ice thickness important? Well, total ice volume is important. If we don't know how much ice is there, we don't know how much potential there is for a total amount of sea level rise from these mountain glacier systems that are changing so rapidly. And I should mention a paper that came out a little while ago looking at the Juneau Icefield suggested that if we continue business as normal for carbon emissions, it's a potential to lose about 68% of the Juneau Icefield. So it might become the Juneau Fjord Research Program. If anyone is into boating, we can turn it into that in a few years. Another big question on the science community that we're chasing is water storage in systems. We have what we call internal water storage. We have a mass balance, which is a mass gain on a glacier system or mass loss on a glacier system, which we traditionally measure by surface elevation changes and kind of monitoring the winter snowpack every year. But in temperate systems, that's challenging because you have basically melt on the surface that works its way down into the lower layers, and it's stored there. We don't know how long it's stored there. We don't know the extent of its storage. We don't know if it reaches the bed and if it just sits in the bed for a long period of time. We have very little spatial and temporal information about this, right? And we're just getting to the point where we're starting to understand how those things are changing. So this is a 3D grid, radar grid, that we collected last year. And I have arrows pointing this aquifer. I'm going to flip forward and it'll all turn to red where the aquifer is located. It's basically a glacial, a firn aquifer with a whole bunch of water sitting there. And we plan on studying that this year. How do we know it's an aquifer? Well, we drilled a bunch of holes and collected some cores and actually found water draining out of it to ground truth that radar data. Why is that important? Well, Greenland has thousands of kilometers of aquifers. We know that there's multi-year aquifers that are basically just sitting in Greenland, and we're not really sure how long they stay there, what their residence time is, how much water's there, and the potential for mass flux downstream to contribute to sea level rise. So we have the potential in Juneau Icefield, which is about 1/10 of the price to study versus going to Greenland to actually study those processes in situ. So I mentioned we had several funded science projects this year. I'm going to flip through these relatively quick, but we're excited to have science teams come to the ice. We've set the program up where we have teaching faculty and research faculty. The teaching faculty basically are working with our students, but they're integrating with the research teams to provide students real research experience. The research teams are excited because they have a bunch of students helping them out. And I'll quote a scientist that was with us last year from Vermont that basically said he got a $500,000 project done on $10,000 last year with the number of hands and the actual collaborative effort that they're putting into the work by comparison. So pretty phenomenal impact. And I'll touch more on that comment here in a little bit. So some of the projects we're working on, we have a NASA-funded team coming this year. Christine Forman from Montana State and Marco Tedesco, they're using remote sensing techniques to basically try to get at, see if they can pick up signatures of life on icy surfaces. So they're working with our students and our other faculty to do that this year on the Icefield. We have a team that's working on testing a new technique. It's a distributed automated sensor technique, as well as some seismoelectric techniques. We actually have 2 teams coming for this type of work. The distributed acoustic sensing method is basically equivalent of turning a fiber optic cable, a long linear fiber optic cable, into thousands and thousands of seismometers. So the difference is right now we put out seismometers. It's really time consuming. I might put a seismometer in to look at things like ice quakes or ice motion. And then I go 100 meters away and do another one. Well, we lay these cables out that we can run with a snow machine. We have a seismometer every meter, and we leave it there. And we can actually watch things like ice movement in real time. We can watch things like water moving in the glacier system and at the bed. So really high spatial and temporal resolution like we've never seen before. It's used currently in geologic environments, but it's never been used in the glacier system. So we're trying that this year to see if we can be successful with it. This seismoelectric method test is another system that's never been used in an ice setting before. And the premise of using this method is we're trying to get at what is the subglacial material that controls flow of ice systems made of. So we think that we can use this technique, which basically is using a seismic signal. So we basically just fire a shotgun into the ground. It generates a seismic, acoustic source, and it also generates an electrical impulse. And the combination of the electrical and acoustic impulses give us information about the subsurface properties. So we're testing these techniques on the Juneau Icefield first with the hopes of trying to go to Northeast Greenland ice stream in future years to study that location because that drains about 15% of Greenland. So it's a pretty important region. We're excited to have the ice drilling development team come to the ice this year. The video on the left is a borehole that we drilled to 80 meters depth on a glacier in eastern Alaska. You can see there's a whole bunch of water at the bottom of the borehole. This borehole had diurnal fluctuations of water pulsing through as a result of just rapid drainage and melting around the glacier system. One of the problems with drilling in temperate ice is water gums up the drill system. So we have a team coming here to test a new thermal drill that's been used on a place called Mount Waddington for an ice core study. If you heard a few talks yesterday, I think Aaron Chester mentioned Mount Waddington. They're hoping to reach about 300 meters of ice thickness and reach bedrock at the site that we've set them up with. And again, the hope is to use this drill ultimately in Mount Waddington in Greenland, and having student hands, having our facilities available to help them test this drill is a pretty exciting opportunity. We're studying deglaciation processes, erosion processes, tectonic processes, and the interactions of those things. This is something near and dear to Peter Kuhn's research that he's working on. Annie Boucher, who happens to also be our program manager for the Juneau Icefield, you can raise your hand, that'd be great. She's working on this for a master's, but we also have teams from Columbia, Vermont, Purdue Prime Lab, Berkeley Geochronology Center, Tulane, and Potsdam working on different components of these interrelated situations. How does deglaciation affect isostatic adjustment? How do glaciers erode? How much erosion do glaciers cause in different locations, different environments? How about mass redistribution of erosion into different locations and causing tectonic changes in the stress state environment? Those are the types of questions we're pursuing as a collaborative team from a geologic standpoint. And then, of course, glacier kinematics and dynamics. We're really interested. This is a glacier program as well, obviously, and we focus a lot on glaciers. And there's a lot of basic phenomena we still don't understand about glaciers. We still use relatively simple flow laws for glacier systems for most environments. So just actually watching glaciers move, learning more about glacier movement over time periods is going to provide us a lot of information. So we're using some pretty sophisticated methods coming up this year. We have one team coming from MIT that's designing a drone that will fly for about 6 hours flight time that will have LiDAR and structure for motion capabilities to map in really high resolution elevation structures, really high resolution changes in those structures spatially over time that we can then relate back to stress and strain deformation states that are important from a glaciological perspective. I've mentioned glacier hydrology. I'm going to throw this in here. We're jumping into the future now, a little bit more in the future. And these are some proposals that we've submitted. I submitted a career proposal to basically conduct a really high resolution study using a lot of these techniques at one location on the Juneau Icefield. It's called Lemon Creek Glacier. And the concept is we have a glacier lake that drains every year. We want to see how that water moves through the system. As that lake drains, we expect the system dynamics to change over time as the water's moving through the system. The interesting thing about this opportunity is that we have the potential to have 250 students in the field over 5 years for this project. That's a pretty enormous impact for students to get field experience. I don't know very many programs that would have the potential for something like that. That's a pretty phenomenal chance. And you can see there's a pretty big list of collaborators here for that opportunity. I've mentioned that we want to separate the program. We want to have multiple programs going. This year we have 32 students that are combined high school, undergraduate, and graduate students. We had 21 students on the wait list. We already have 7 students that are deferred and on the enrollment for next year. already. We had about I think just shy of 80 students that applied this year. And it's really the first year that Annie and I have been trying to market the program as often as we have. I think there's a lot of potential ties at the University of Maine. For example, we're starting to build ties with Upward Bound and Maine Bound. Upward Bound provides on-campus support for high school students, first-generation high school students. And the idea is possibly we can work with them and Maine Bound, who does outdoor education type programs, to build college recruitment and retention programs using JERC facilities and JERC resources. We've also talked about specific graduate student research projects on the Icefield and focused research that graduate students and faculty can kind of design. So for example, we've been talking with Iris Pascal about developing glacier seismology workshops on the Icefield. So these are the types of things that ideally can help us advance our knowledge of the techniques, tools that we're using, and our physical knowledge of the environment that we're studying collectively, while giving some pretty amazing opportunities to students. One thing we're doing this year and last year, we're trying to support as many masters and PhD students as we can. So there's some pretty funny pictures here of our masters and PhD students. Annie here, Lynn is sitting right over here, did not do her PhD here, but she got 2 years of teaching experience on the Icefield, which is a great experience. Elizabeth from Columbia is using the Icefield work for part of her PhD work. Michaela from Ohio State, this is going to be her first year teaching on the Icefield and her first teaching experience. Allie Balter, some of you might recognize, she did her master's here and she's working at Columbia now, and she's using part of this work as her PhD. And then Donovan Dennis is also working on this as part of his PhD work at Potsdam. Postdocs. This is a big push for us. In my career grant, we had 3 postdocs, these postdocs at the top. Ibai's from Spain, I's at University of Oregon, Brad's at Caltech. Liz Alti just basically is working with Brent Minshew as a postdoc advisor at MIT, but we're trying to suck her into the program. And then we recently submitted a 3-year proposal with Calvin Shackleton, who's at University of Tromsø. The proposal submitted to Norway to hopefully have him come to Maine for 2 of the 3 years and build relationships between Norway, University of Maine, and the Jingoistic Research Program, and have a full-time postdoc basically stationed here and working with the program and helping us run the program. And the hope is to have a rotating postdoc that's involved in the program that's basically housed at Maine over the coming years. We've got a lot of public outreach going on. Thanks to Carl and some others. We've had Boston Museum of Science reach out to us recently. We're planning on collecting a lot of data this year. They're putting up a display in the summer of 2020 for Arctic exploration, and a fair amount of visual data sets will likely come from the Juneau Icefield, including imagery, video data sets from the drill site this year, a lot of the geophysical data that we collect, and hopefully building kind of 3D virtual displays for Boston Museum of Science. Also, the Mendenhall Glaciers Visitor Center is redesigning their setup, and they have asked us to help them with basically doing a traverse across the Icefield as part of their display. And the other thing we're doing, we're getting a lot of publicity. We're chasing publicity to try to advertise this program, which I think is good for UMaine. It's good for the program, obviously, and again, it comes back to kind of giving students opportunities ultimately, because the program needs money. This article is written by Ben Santer, who was the lead author for the 1995 chapter on global warming for the IPCC report. So he's been around for a long time. And this was an article written by Drew Higgins, who was our artist-in-residence science communication person, talking about how the Juneau Icefield is trying to build this supportive environment and this collaborative environment. And I couldn't help but throw this picture in here. Is Dan even here? Dan, he is. We were joking yesterday that we couldn't find any recycling bins around here. So he basically was stealing the can out of the trash bin. I think one of the future things we really need to do on the Icefield is not just talk about the science we're doing. We need to make sure our students and our faculty are going home and trying to build solutions into the equation too. So the hope is to start having more of a sustainability communication process on the Icefield, where all of our students, all of our staff go back, all of our faculty go back and say, okay, well, these are the types of things we can initiate back in our communities themselves, because I don't think it's enough anymore to just do the research. I think we gotta, this is a really good chance for us to take a new program that we have at Maine and really make a difference worldwide with our students that are traveling around the world and going back to their home communities. And so with that, I'll leave you with this slide. My ultimate goal for this program is really to make it an international hub based out of Maine and tied very closely with University of Maine. To do that, as part of that, I would love to make it free for all students. You can imagine it's not cheap to get students across an Icefield. It's pretty pricey. But right now we have UMaine Foundation signed on to help us build an endowment. So we're chasing a couple proposals coming this year. We also have an organization, a marketing organization that's offered to basically provide up to $250,000 pro bono to help us market the program over the next few years. So that's a pretty big win for us. And the thing that I mentioned we aren't doing good at, I mentioned we're doing well with kind of male-female diversity in general, but really we're not reaching the underprivileged students. You know, there's over 100 historically Black universities in the United States. And I think I saw numbers of maybe 10 African Americans graduating with a PhD in earth sciences last year. Pretty abysmal. There's 32 native colleges across the United States. And the same thing applies basically. So we could do a much better job reaching those communities. And I think this is the type of program we can do that with. And I'd like to see that happen. And I'd also like to see that this becomes an alternative for future collaborative research. You know, when I think about NSF, when I think about NASA, they're kind of naturally hamstrung by a bureaucracy. You know, we're all competitive with each other. This environment's not like that. We're basically pitching in to kind of help each other out to make this fly. I think this is a really good working model that we can use as a community to kind of set the stage moving forward and have Maine and JERP be basically a leader in kind of forward thinking of collaboration in the future. So with that, please do check out our website. You can learn a lot more about the program there. Happy to take questions. And I think, just a show of hands, there are a few JERP people in the room. Who's been to JERP or who's going to JERP? So 1, 2, 3. Mira's going. Quinn's been. Carl's been. All right.
Peterson is daughter.
Yeah. Peterson is us. So we're working on building the network. So if you're interested in the program, if you want to learn more about the program or have research ideas, collaborative ideas, please come see me because we're always looking for those types of developments. So.
Seth, that's a really great initiative. A couple questions. How do colleges and universities become involved in this, and what is the application process for students?
So the application process is, well, so we'll start with the application process. It's basically almost like a college application form. They provide pretty extensive details, their academic background, they provide a CV, they provide a few letters of recommendation currently. In terms of universities getting involved, it's really just them coming to talk to Annie and I. So the best thing is to have them point them to the website and have them email us. The goal is to make it, to bring people into the program. The biggest crux that we have is funding, and that's the thing that Annie and I juggle all the time. I didn't go into the details of a lot of the other behind the scenes work that's going on. We have an academic council, we have a science panel, a bunch of senior scientists involved in this process that are helping us brainstorm some of these science ideas. So there's a lot of behind the scenes that people can also get involved in. So really it just starts with them coming to talk to Annie and I. We're a pretty small business in terms of number of people that are actually paid to work for the program.
In general, what does a participating student end up having to pay?
That's the crux. So the participating student is paying about $10,000 to participate. So that's the academic credits here, and that's the field cost. We traditionally give enough funding to cover 2 to 3 students for tuition, special needs students that don't have the financial capabilities to cover the tuition. And that's been the crux of the program. You know, a lot of the students that have come to the program traditionally come from the schools that have the money to just pay the entire cost. And that's what I'm trying to combat. You know, I'm thinking about the community that I grew up in. I don't know if you saw the the note, three out of the 25% from where I came from went to college. Yeah, we would never have been able to afford that. So I'm thinking about that community, that first generation college student, small town Maine community, small town, any small town community, as well as the underprivileged. So that's where the endowment is really important. I will say that the operating budget, it kind of blows me away. I think if you could capture a big donor, for a $5 million endowment, this could revolutionize the opportunities you can give to students in the field. I really think that. Thanks. Cool. All right. Thank you.
All right, thanks, Seth. That was fascinating. And I'd write you a check if I had funds. Actually, I'd write you a check for $5 million. Maybe next year. I'm looking for tax deductions. Okay, a few items standing between us and lunch. These are good items. First of all, we're going to go through our Symposium awards. Let me thank first the judges, Dan Sandboys, Jacqueline Gill, and Jim Roscoe for their work on this. I think I can speak for them to say that it was a difficult job. Thank you to all the students, both the oral and poster presentations. The quality was amazing. I think the Bourne Symposium over the years has had a very high bar, and I'm glad to see everybody jumping well over it. So this was a tough job, but we had to convene on some decisions. So let me start with the Bourne Symposium Best Student Poster Award. It was such a hard job that we decided to co-award it to two students, Mariana Miles and Alessandro Miraghetti. And if you could come up, I've got your awards here.
Do you want a picture?
Marie's in class.
Yeah.
Okay.
Carl, get a picture.
Okay. Okay, our next award is for the Best Student Oral Presentation Award. And again, we're awarding it to two co-awardees, Mario Williams and Mario Mandrayak. Okay, next is our CCI Student Outstanding Service Award. This one is going to go to, again, co-awardees, Anna McGinn and Will Kaczynski. And we gave this because the judges have been amazingly impressed by the World Climate Simulation and their efforts to put this together and get it out into local schools. I know they're doing it many more times this spring, but I know on May 17th, they're going into Oregon High School to do it to the entire 9th grade class. So I encourage you, Maine, to make the most out of that. Bring everything they've got to document it. So congratulations.
We welcome volunteers.
And our last award is the Churchill Award for Outstanding Exploration. So our first several talks of the symposium were given by previous Churchill Award winners presenting the research. And again, all outstanding, but we had to choose one. And this year's award goes to Anna McGinn. And while I've got the stage, since our last award was for the Churchill Award, and Dan is here, thank you, Dan, obviously, for supporting this program over the years. Somewhere I have a spreadsheet with all the students that have gotten Churchill exploration funds. I think it's over 70 by now. And this year's award winners for 2019 are Megan Spoth, Annie St. Mond, and Scott Braddock. all for their projects. So congratulations. Okay. So now for a few thank yous for the symposium. The graduate students for moderating all the sessions. Thank you for that. Aaron Chesler and Anna McGinn were taking pictures, obviously, so thank you guys for that. Mark Breuer and Andre Kurbitoff did the AV stuff, which I assume has been seamless, like it always is. So thank you guys for your assistance with that. Thank you to the judges again. And then finally, of course, I think you all know, we need to say a huge thank you to both Betty and Becky for putting this together. I imagine most of you saw this, but in case you missed it, Betty was awarded the 2019 Outstanding Research Administrator Award. So a heartfelt thank you to both of them, not only for Board Symposium, but for everything that you guys do for us. I think CCI functions the way it does largely in part because of you guys. So thank you so much. Between us and lunch is a picture. So Becky is organizing a group picture at the back of the room, so follow her lead, I think.
Pressure's on.
No, that was a good session.